Chapter 10 is about the Lewis model for chemical bonding. So, I think medical technology today is absolutely amazing. It's science fiction as far as I'm concerned, especially with the mRNA technology that we can code mRNA to make proteins that do certain functions inside of our bodies. This is absolutely amazing. And we also design drugs. And one of the diseases that has been greatly researched is HIV. And some of the drugs, for instance, protease inhibitors, they go and they change part of the virus's life cycle. So they're looking at the protease protein and the step for the HIV replication. So it's very interesting how they were able to do this. And there's different types of bonding theories. Lewis theory, it's actually wrong. Here I am telling you, okay, we're gonna learn this theory, and it's wrong. But it's a very good model and explains quite a bit. And the best model is quantum mechanics and molecular orbital theory, and kind of all those combined. But Lewis model makes quite a bit of sense and explains most things, and it works very, very well. And so the next two chapters will apply this quite in detail. But again, this is not the perfect thing. It's actually, like I said, it's incorrect. But also, like I said, it's extremely useful and explains certain things, like water, why it's two hydrogens and one oxygen and not one hydrogen, one oxygen, or three hydrogens and one oxygen. And although there is the hydronium ion, H3O plus, and the hydroxide ion, usually O is first, OH minus, so we do have those, but those are charged. We can also predict shapes of molecules, especially more next chapter. And we can predict some properties using Lewis model. So it's a very powerful theory. And so Lewis, he's where I got my PhD. He was a professor at Berkeley. And he came up with the idea for basically the octet rule. Of course, he was wrong by several things. He thought atoms were like boxes, and the octet rule was from the 8 corners of a box. And that's where that's his basis for his electron dot structures. So if you look into his notebook, he drew atoms like little boxes. So he was right about the number 8, but not for the reason like the corners of a box. But it's a very powerful theory. And so why do atoms bond? Well, they bond for low energy. The idea. So they bond for lower energy. But there are certain areas where there's lower energy, and the area of lower energy is quite frequently 8, specifically 8 valence electrons, 8 outermost electrons, and that's the configuration of noble gases. And and it's 2 for some hydrogen and helium. It's 2. Well, helium tends not to bond very frequently. And the reason why it's the energy is this low. If you look at all the electrons interacting with the protons, the nucleus, and it turns out that those bonding schemes are lower in energy, specifically potential energy, than other configurations. But in order to calculate this, there's the repulsion between the nucleus. So nucleus are positively charged, and when things bond, the nucleus are close together. So the nuclei repel. The electrons themselves repel, and there's what keeps it together. Then, well, it's the positive nucleus and negative electron cloud, and the electrons in the electron cloud, the attraction between them. That's what keeps things bonded. But it has the other repulsions trying to break the molecule apart. And then, generally speaking, if the attraction between the positive and negative charges are greater than the repulsion between the like charges, then the bonding scheme, and also there's very low energy, then the bonding scheme works. And these are different types of bonds. So metals and nonmetals tend to have more ionic bonds. They can have covalent bonding between metals and also between metals and nonmetals. Generally speaking, though, the bonds tend to be more ionic, where the electrons are transferred from one atom to the other. Nonmetal and nonmetals tend to have covalent bonding. This is where electrons are shared or unequally shared, as we'll learn later. And metals, they tend to have metallic bonds. Metals can have other types of bonding as well. So metals can have covalent bonds with themselves and with nonmetals, but metals tend to have more metallic bondings where it's kind of a sea of electrons. So here are images showing the different types of bonding. Ionic bonding, where you have electron transfer and you have whole charges. By whole, I mean times that of the charge of electron, the 1.6 times 10 to the minus 19 coulombs. Negative for electron, positive for proton. Covalent bonding involves sharing or unequal sharing of electrons between atoms. And metallic bonding is where you have positive centers and then electrons that flow between the positive centers in a sort of a sea of electrons. So for ionic bonds, when an atom loses electrons, it's called a cation. So not cation, cation. And if you have a hard time remembering if it's positive or not, think of the T as a plus sign. And generally speaking, the metals tend to have lower ionization energies, so it's usually easier to rip an electron off of them. When nonmetals gain electrons, it becomes an anion, and the nonmetals tend to have high electron affinities. That's the energy that's released when electrons are added to it, so it tends to favor the anions towards the nonmetals. And now when you have a metal give its electrons to a nonmetal, now you have two opposite charges. Now they attract to each other, and that's an ionic bond. Covalent bonds, these are sharing nonmetal atoms. It's difficult to remove electrons from them, but when they bond together, they tend to share electrons. And then the electron clouds between them and molecular orbitals, which we'll learn later, they're attracted to the nuclei of both atoms. Metallic bonds, these low ionization energies, they allow electrons to move very easily, and metals tend to be conductors, and also the conduction band, the energy levels just above the occupied energy levels, they tend to be just at the valence band where the electrons lie, so it's really easy for electrons to move along a metal surface. And I mean, of course it is because they're conductors. So the electrons are really easy to move, and then you tend to have more like an array of metal cations, but then this sea of electrons between them, and this whole thing is not charged. So I say that they have the cations with all the sea of electron between them, but there is at any given time enough electron density around each of these cations that it's as if it was neutral. Well, it is neutral. And this is important, though, because there's certain properties of metals, and the electrons can flow in metals, and there are certain consequences of this. For instance, within a metal, there is no electronic field. So if you're trying to zap someone with a lightning bolt, there's something called a Faraday cage, where if the person is surrounded by metal, not even completely in the terms of a cage, then there's no electronic field within that cage. So if you're in your car and you get struck by lightning, people think it's the rubber tires. No, it's actually the metal frame of the car that protects you. It's called a Faraday cage. But coming back to chemistry, this sea of electrons, it forms a metallic bond. Also the other properties of metals, which I mentioned, like the Faraday cage. And I've already explained what's going on here, this sea of electrons. And something you can see here, the metallic bonding. Metals are also ductile, they're bendy. And compare that to ionic bonds that are not, they're brittle. So you can move metals around, and it doesn't change their bonding scheme at all. So they're very ductile and malleable, whereas ionic compounds are brittle. And because the ionic bonds, if you move them around, you break the bonding scheme. Whereas metals, if you move them around, you keep the bonding scheme. So that explains also physical properties of metals. So which of these compounds is most likely to contain ionic bonds? So ionics can tend to be metals and nonmetals. And the metals and nonmetals is going to, it's C, it's magnesium fluoride. Magnesium metal and fluorine is a nonmetal. So valence electrons, these are the outermost electrons, and these are the ones that are held most loosely. So it's easiest to remove these. And for chemical bonding, it only looks at these surface electrons, these outside ones, the valence electrons. And because of this, the valence ones are the most important for bonding. And it's also the reason why we have the periodic table arranged the way we do. We have based off of the valence electrons. And Lewis theory looks mostly at these valence electrons. So how do you determine the number of valence electrons in an atom? It's the group moving across. Alkalis have 1, alkalines have 2, boron family has 3, and only where carbon has 4, and so on. The transition elements, they all have 2 valence electrons. Why? Because of the principal quantum number. Remember that with the rows? The principal quantum number is higher for the s orbital than it is for the d orbitals in the transition metals. So the Lewis structure, we model the electrons as dots. So electrons are not dots, they're sort of this fuzzy cloud that has a magnetic and electronic field and a little bit of mass associated with it. That's what an electron really is. But we're going to have them be dots for now with the Lewis theory. And then including these dots says how many valence electrons. So lithium has 1, beryllium has 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon 8. And so you start with the first 4, you put an electron on each side, then you start pairing them up for then after that, after 4 for carbon. And as I mentioned before, things bond because it's low energy, more stable. So more stable, you're more likely to sit around for a while. And the chemical bonds, it's either transferring or sharing electrons. And usually the electrons are shared or transferred in regards to the octet rule, where 8 is a very stable configuration. There are some exceptions. So much of it's beyond this class. Boron, for instance, is kind of in a category on its own. And hydrogen, we do mention hydrogen. Hydrogen tends to go for 2 instead of 8. Now, which electrons are removed? So for potassium, and if you remember when we were talking about ions, electrons are removed from the highest principal quantum number first. So the potassium here, the electron that's removed is the highest end, the 4s1. It's removed there to form the potassium plus 1 ion. But now this has the noble gas configuration of argon. So and things tend to bond towards that stable octet. In this case, it's for argon's configuration for potassium. And where does this electron go? Well, for a salt like calcium chloride, potassium chloride, the electron is transferred from potassium to chlorine to form the chloride anion, say the potassium plus 1 ion, chloride anion. And now they both have octets. They both have noble gas configurations. And as mentioned before, it's the octet rule. And the octet rule is based off of the noble gas configurations. And this also, we can predict the formulas of ionic compounds because the electronic balance needs to be the same, meaning plus 1 minus 1. And if it's a plus 2, there has to be 2 negative ions to counteract the plus 2 charge. So there has to be a balance, I should say. There's a balance of charges. And this can also help us predict the relative strengths of ionic bonds using Coulomb's law. Coulomb's law, if you recall, is the constant. The force is a constant times the charge of one over the times the charge of second all over the distance squared for the force, or the potential is just it's the distance to the first power. It's squared for the force, and it's rare that you have two. You're going to have many, and with many you have a crystal lattice. And the crystal lattice, it's a whole bunch of positive and negative charges. And the crystal lattice, there is an attraction between the positive and negative ions, and there's repulsion between the like charges. So it's a picture of that. So with for sodium chloride, for instance, here is the that's like gaseous sodium and chloride ions. Then it forms a solid, and this is the lattice. It's the organization of this structure, and they organize in very particular fashions. And there's quite a bit on this, and you can study more if you want on this. There's something called the Madelung constant, where it looks at the certain structure. And there's different structures for different temperatures. Also, you can have atoms that are removed, and it changes some of the chemistry of the surface. So there's quite a bit of further advanced topics you have for this. But for right now, I want you to understand the lattice energy. It's the energy released when you have these ions come together, and it's all simple geometry. To be honest with you, it's really simple geometry applied over and over and over again, where you have the attraction between the unlike charges and then repulsion by the like charges, and that combined with a bunch of the Pythagorean theorem, you can calculate this all out. And there's stability from this, and this is the stability from the salt forming this lattice is the lattice energy. And the lattice energy is released, and it's always exothermic. And so delta H, if you remember, is path independent. So since it's path independent, we can apply things like Hess's law to calculate it out. And so this is just an application of Hess's law. And the Born-Haber cycle, this is that application of Hess's law to go and calculate out the lattice energy. And the idea with this is we have a certain set of known things that happen, and then we have our unknown step, and it's the lattice energy is the unknown step. And if you have all the other variables, if you know everything else, you can calculate that lattice energy. And here's a picture of that. So start off, you have sodium metal, and in this case, 1/2 chlorine gas. And it's not proper, but trying to make it simple for the formation of sodium chloride. So we start off with those reactants, and then we have the product, sodium chloride. And we can measure that reaction, that heater reaction, very easily. So we can also take sodium. Now, following this chart, you can go from sodium solid to sodium vapor. That takes energy. You can go from chlorine gas to a chlorine molecule, like a single atom. That takes energy. And you can also rip off an electron from sodium, and now you have sodium vapor gas. So that's all endothermic. And then you have an exothermic step here where you have the electron affinity of chlorine, and then chlorine becomes chloride. And now we have sodium ion vapor, chloride, and ion vapor, and then this missing step here, the lattice energy. But if we know all the steps and the overall reaction, with the exception of the lattice energy, we can calculate that out. And that's the idea with the Born-Haber cycle. And knowing all those, we can then calculate it out and get the sodium chloride lattice energy. In this case, it's negative, so negative exothermic, 788 kilojoules per mole. Now that you know what the lattice energy is, let's talk about the effects that things have on it. So specifically the ionic size and also the charges of the ions. So starting off with ion size, generally speaking, the larger the ions, the weaker the bonding between them. Because remember Coulomb's law, it's a charge of one, charge of two, all over the distance. So a bigger distance, so the distance is in the denominator. Well, it's for the force, it's distance squared. So a bigger distance and distance in the denominator, so a bigger number there makes an overall smaller number. So to illustrate this with the different chlorides, so chlorides staying the same, but the size of the cation is changing, and it's getting bigger. As the cation is getting bigger, the lattice energy is going down. So not surprising. Now the ion charge, the larger the charge, the larger the attraction. So that means that if we have a bigger charge, there's going to be a much greater attraction. And if you compare sodium fluoride here to calcium oxide, we have +1, -1, and +2, -2, and they're about the same length between them. So it's a charge of one, charge a second. So from this, you would expect calcium oxide to be 4 times stronger than sodium fluoride. And in this case, this is close to the truth. And for these factors, the ion charge is usually the more important factor. So, and the theory implies these attractions of the ions are strong, and they also since it's strong, that means it has a high melting point. So, in order for something to melt, so go from solid to liquid, you have to add enough energy to break the bonding between the ions. And so that's predicted, and it's actually, and this is reality. So ionic compounds have very high melting points. I've never seen molten salt, sodium chloride salt, for instance. This is something I have not seen with my own eyes. I've seen salt get so hot it glows red, but I have not seen it melt. So, and because of this, ionic compounds are solids at room temperature. And rocks, for instance, rocks and minerals. Rocks are a combination of minerals, and minerals are compounds. The rocks, because they're always solids at room temperature, so you don't see molten rock there. I have seen it living in Hawaii. You can see the lava, but that's very, very hot. So the electrostatic attraction is non-directional, so it's not just two things, it's many. Because of this, we don't have ionic molecules. So it's a simple ratio, and it's really a lattice. So that's the idea of ionic solids. It's just, and we have sodium chloride, NaCl. It's just, relatively speaking, 1 sodium to 1 chlorine in the ionic compound. And mentioned before, comparing to metals, ionic compounds, they're brittle. They're hard and brittle. They're not bendy like metals, and they tend to be solids. Actually, they're all solids at room temperature, and they have very high melting points. The liquid state conducts electricity because the ions are flowing between them, but the solid one does not. The ionic compounds that are soluble in water, they conduct electricity, and we've mentioned this before about electrolyte solutions. And so here's sodium chloride, salt, and you can melt it. The ions can move, and now these ions can conduct electricity. So the Lewis model predicts the high melting points. This is true, and also many of the things that we've said before. If half the ions displaced from the positions, the repulsive force should occur. That's the reason why the ionic compounds are brittle. So you pound salt and it breaks apart, and they shatter. So this is all predicted with the theory, and it's also true. And for something to conduct electricity, there has to be charged particles that can flow. And so that means that a solid, the ions don't flow, so therefore the ionic solids don't conduct electricity. But molten ionic compounds can, as do the aqueous forms of them if they're soluble. So mention that there. So if you try and so this image here shows putting 2 leads into salt. Nothing happens, but you put it in salt water, it does conduct. That's proving the properties of electrical conductance, conductivity of ionic compounds. So use the ionic bonding model to determine which has the higher melting point. Sodium chloride and magnesium oxide. Explain the relative ordering. So NaCl is +1 -1, MgO is +2 -2, and it's the charges. The charges are more important, so magnesium oxide is going to have the higher melting point. So that's with this one here. So Lewis structures, Lewis bonding, it's a simple, I told you, it's an incorrect theory. This is all wrong, but it's a great model. And we're teaching you the model, and I must say, I look up Lewis structures still. Whenever I'm looking at something, I'm like, oh, what does a Lewis structure look like? I mean, for instance, I have a sulfa allergy to drugs, and by looking at a drug's Lewis structure, I can determine whether or not I personally am allergic to that drug. So it's still this is using Lewis theory, so it's a very powerful theory. And looking at the valence electrons, where the nonmetals, they when they covalently bond, they're trying to get towards an octet, so 8 electrons, with the exception of hydrogen just wants 2. So, and when electrons are shared, we call it a covalent bond. So the electrons, they are shared by atoms called bonding pairs, and there's the bonding pairs, and then if an atom keeps its electrons to itself, that's known as a lone pair or a non-bonding pair. So looking at water here, HOH, H2O, HOH, there's a bonding pair with the hydrogens and the oxygen, but oxygen also has 2 lone pairs. So oxygen has 2 bonding pairs and has 2 lone pairs. The hydrogens just have 1 bonding pair each. Well, the hydrogens are happy, they get their 2, and oxygen's happy, it gets its 8. So the octet rule is preserved, or the duet rule for hydrogen. So that's how the bonding scheme works. So for single covalent bonds, this is when 2 electrons are shared. So 2 electrons are shared. This is known as a single bond between 2 atoms. And mentioned before, the oxygen in this bonding scheme gets an octet, and the hydrogens each get a duet. So if 4 electrons are shared, this is known as a double bond, double covalent bond, or simply a double bond. So 2 oxygen atoms coming together to form diatomic oxygen. You can see that with the 4 electrons shared, each oxygen atom is sharing 4 electrons, and they also keep 4 to themselves. So it is a double bond, and it fits the scheme because the octet rule is still preserved. Triple bond, this is where 6 electrons are shared, and for nitrogen, diatomic nitrogen, 6 electrons are shared, and each nitrogen keeps 2 to themselves, so each nitrogen atom has 8 electrons. So this is a triple bond. And the Lewis model implies that some combinations should be stable and others should not because of octets. So using these ideas, we can predict what formulas and molecules of covalently bonded substances will occur. And from this, hydrogen and the halogens, these are all diatomic. So 2 atoms, as predicted by molecular theory. But there's other diatomic ones. Oxygen can form 1 or 2, and this is also predicted by Lewis theory. But there are some compounds which oxygen has 1 single bond, and where it has a triple bond, and it still has an octet. So this is there's more to meet this is more complicated. So we'll go over through some of the complicated parts of this. So oxygen tends to bond with 2. But there are certain cases like the hydronium anion, where you can see here it bonds to 3, and that brackets around the H3O plus, the bracket around the molecule there that shows that this entire molecule has a positive 1 charge. So, and the H3O plus, it's missing an electron because that would break the octet rule. So, and okay. So why would we have certain molecules form and other ones do not? And the idea is the octet. So H2O is stable, H3O should not be because it breaks the octet rule. And this is in fact correct, but then also predicted is H3O plus should be stable. And in fact, it is stable. That's what acids do. They turn water into H3O plus. And unlike ionic bonds, covalent bonds are very directional. So meaning they're in a very set area. The bonding is between these 2 atoms only. Well, that's not entirely true. We'll learn that later in molecular orbital theory. It can be true, but in molecular orbital theory, the bonding can be spread out between many different atoms. But I know I'm jumping ahead. I don't like teaching incorrect things. If you're wondering why I'm teaching this, and I'm telling you why it's wrong. So this is mostly correct. And Lewis theory, we focus more on individual molecules for covalently bonded compounds. So versus the lattices for anticompounds. And nonmetals, they have individual molecule units. So and the numbers are important. Where you have the ionic compounds, it's more the ratios. The individual atoms are important because you get different molecules if you have different numbers of atoms. So, for instance, we mentioned empirical formulas, the CH empirical formula, you can have acetylene, which is C2H2, and you have benzene, which is C6H6. They both have the ratio of 1 to 1 for carbon to hydrogen, but if you have different numbers, it's going to change the molecule. And also with the, this is more intermolecular forces instead of intra. So we'll talk more about the forces between molecules. Molecules tend to have lower melting points. So because of this, you can see molecular compounds in all 3 states at room temperature. So, and for things like hydrocarbons. So you can find lighter gases like methane and propane being gases at room temperature. And you can have octane 8 carbons be a liquid at room temperature. And then you can have really heavy paraffin waxes and asphalt that are like 20 carbons and above, or could even be high. Well, they can be much higher than that. So really, really large number of carbons, and they're solids at room temperature. So you can see this with hydrogen and carbon. So the molecules are there. So we have a wide range depending on the size of the molecule. And so molecular compounds are very hard and brittle, but looking at the attraction between the molecules, intermolecular attractions, but the molecular solids, they are brittle and hard, but they can also be soft and waxy. So like ice, for instance, solid water is brittle and hard. But then you have paraffin waxes and asphalt that you can shape. So they can flow if you put enough pressure on them. And this also suggests that molecular solids and liquids should not be able to conduct electricity. So since there's no charged particles, they can't conduct electricity. So of course there's exceptions to this. So certain types of carbon can conduct electricity. So graphite, it's like a single molecule that can conduct electricity. Actually, DNA molecules conduct electricity. But generally speaking, this is true that covalently bonded molecules do not conduct electricity. There's tended to be, the other ones are more of exceptions to the rules than the rule itself. So looking here, this is pentane, and pentane has very strong bonds within, so intra the molecule, intramolecular forces. Then intermolecular forces, these tend to be weaker. The weaker bonding between there means it's going to have certain characteristics: low melting points, uh, low boiling points, etc. from this weak attraction between the molecules. So what's wrong with this statement? Atom forms bond in order to satisfy the octet rule. So, and nothing in the statement is correct. That's not true. Atoms form bonds for complex reasons that include the lowering of potential energy. The octet rule helps us predict which case will form. Yes, that's true. C, atoms form bonds for complex reasons that include the lowering of potential energy. The octet rule is not really useful. Well, if the octet rule was not really useful, there's no reason why we teach the Lewis theory. So it's B. This is the reason why the octet rule is a very powerful tool, which is, in fact, like I said, why we teach it. So electronegativity. So what is electronegativity? It's the ability of an atom to draw electrons to itself. So certain atoms are very, very good at drawing electron density to itself. Fluorine, for instance. Fluorine is a +7 charge, and it's a small atom. So because of that, fluorine is really good at drawing electron density to itself when it's bonding. And so combine that with hydrogen. So hydrogen and fluorine, when they bond, what happens is that the fluorine draws, so you should say, oh, it's equal sharing of electrons. Not really. The fluorine is pulling more electron density away from the hydrogen, and then it forms what we call a polar covalent bond, where the hydrogen end is electron poor, and it gets a partial positive charge, and the fluorine is got extra electron density, and then that we give it a partial negative. So what do I mean by partial? I mean less than 1.6 times 10 to the minus 19 coulombs. That's the charge of a proton and electron, respectively, but opposite charges, of course. So here with the hydrogen fluoride, you have the electron density flowing from the hydrogen to the fluorine, and then because of this, you have the partial positive charge on hydrogen, partial negative charge on the fluorine, and there's a polar covalent bond. And it depends on the atoms. So most bonds, there's some degree of sharing and some degree of ion formation to them. So it's kind of it's a spectrum. It's a continuous spectrum, and it just depends on how much of the electrons hang out around one atom versus the other. And for a perfectly equal sharing, we call it covalent. For unequal sharing, we call it polar covalent, and then for complete transfer, we call this ionic. And it has to do with electronegativity. So electronegativity is the same trend as ionization energy, first ionization energy, with the exception of it stops at fluorine. So helium has the highest first ionization energy of any of the elements, but fluorine, the noble gases don't have that much electronegativity associated with them. So fluorine is the most electronegative element. And that would put at the other opposite end, francium is the least electronegative, but francium is also very radioactive. It's very unstable. It's not around for very long. So, and we don't give noble gases assigned values because they're not very good at attracting electrons. So, opposite of atomic size trends, same as ionic first ionization energy. And generally speaking, the larger the difference in electronegativity, the more polar the bond will be. And the more electron density is around the more electronegative atom. So here, this chart shows the electronegativities of the different elements, and noble gases are not included. So fluorine is the highest, and this is also Pauline's. This is Linus Pauline's electronegativity scale. So Linus Pauling came up with these. There's other electronegativities, and We usually just call electronegativity, or it's really Pauline's electronegativity. And you can see there that fluorine is the best and francium is the worst. Or you could say francium is the most electropositive. You've also used that term as well. So arrange these elements in order of decreasing electronegativity. So highest first, then lowest. So it follows the same trend as the opposite trend. Yeah, same trend as first ionization energy. So the highest up is, and furthest to the right, that's nitrogen. Right below nitrogen is phosphorus, and then to the left of phosphorus is aluminum, and then sodium is far over as an alkali. So it's going to be nitrogen first, then phosphorus, then aluminum, then sodium. Is that. So if the electronegativity difference is 0, this is called pure covalent. So this is between two elements, two of the same elements. If there is a difference of electronegativity between 0.1 and 0.4, this is nonpolar covalent. From 0.4 to 1.9, this is polar covalence. And then if it's above 2, a difference is above 2, this is known as ionic. Why is this? Why do we care? Many of you are taking organic chemistry, and the bonding between hydrogen and carbon is considered nonpolar covalent. So that's the main reason for this, is to give organic chemistry the ability to say what it does using Lewis theory. So in order for Lewis theory to work with organic chemistry, that has to be true. And this just mentions what we just had spoken about. And with these non-polar covalent bonds, and organic chemistry will talk more about this, although they do contradict themselves occasionally. What would chemistry class be with a little contradiction, right? I'm doing it several times in this video, for instance. So in organic chemistry, they say that carbon-hydrogen is a covalent bond, but then oxidation or loss of electrons is when hydrogen is removed, and which means hydrogen, therefore, is an electron donor. So hydrogen donates the electron density to carbon under the bonding scheme. So it's really, it's an unequal sharing, but organic considers it to be equal. So, but then this just illustrates the unequal sharing is polar covalent, and then complete transfer is ionic. So dipole is it's the measure of bond polarity. It's just a positive one end and a negative on the other, and it's just the charge times the radius. And this is not Coulomb's law. This is something measured in dBAs. So generally speaking, the more electrons two atoms share, the larger the atoms are, the larger the dipole moment. So, which makes sense. Bigger Q, bigger R for the dipole. So to give you an example, some of these, chlorine, perfect covalent, has no change electronegativity. Dipole moment is negligible. Well, it should be 0. Lithium fluoride, on the other hand, it's the change electronegativity, and you're gonna have one charge on one end, one charge on the other. The dipole moment is very high. And the percent ionic character, this tells you how much of the bond's dipole moment is compared to what it would be if they were completely transferred. So, and the ionic character, so with the ionic character, there comes certain consequences. It involves things like higher melting points, for instance. And here shows the percent ionic character for various compounds. So in this chart, the percent ionic character is on the y-axis, and the electronegativity difference is on the x-axis. And you can see the various scattered points here. And you have the more covalently bonded ones on the closer to the origin for this, and then you have the ionic compounds further away to the origin in this scatter plot as well. So how do we write Lewis structures of molecules? First, you start off with the skeletal structure. So hydrogen atoms, these are always terminal, and the more electronegative atoms, like halogens, are also placed in terminal. So you put the bigger atoms, like carbon, like nitrogen, like phosphorus, in the middle. So you're saying. And then sum up the number of valence electrons. So sum up the valence electrons is the next step. And then distribute these electrons along the atoms, giving octets or duets to as many atoms as possible. If you don't have enough electrons, add double or triple bonds as necessary to give them octets. And then the last step we'll talk about later is to minimize the formal charge. So there can be more than one type of structure. And if there's more than one type of structure, you can form what we call resonance structures, where there is kind of a half a bond between them. And I should also mention resonance bonds do not always form. So many hydrocarbons, for instance, will not form resonance bonds, and other ones do form resonance bonds. So it is going to be a bit more complicated. I don't want you to think because if there is a resonance structure possible that it will happen. That's not part of the theory. So look at the resonance structure here for ozone, O3. And you have two possible structures that ozone has, and we put these little arrows between them. So there's a resonance, therefore the true bonding scheme is like the blend of these two. And here's a picture. It's kind of like having two dogs and the offspring is a hybrid between the two. Likewise, the two resonance structures, the actual bonding scheme is a hybrid between the two bonding schemes. So which one is not a resonance structure of the ion shown here? Well, let's see here. The one that's not the resonance structure would be B, because the atoms are exchanged. So here you have sulfur, carbon, nitrogen, carbon's in the middle for that one. B, you've had the atoms exchange, so that is one where this is not a resonance structure. Formal charge, I mentioned this before, but a formal charge is a fictitious charge. It's a way of keeping track of where electrons are. We've already mentioned oxidation states. So it's kind of like oxidation states where you're looking to see where electrons are and where are not. In this case, we are looking to see where electrons are as it corresponds to how things are bonded. So for the formal charge, it's the number of valence electrons that an atom normally has minus the number of non-bonding electrons. So each non-bonding electrons, the atom gets all of it, and then half of the bonding electrons. And also, for a neutral molecule, the sum of all the formal charges has to be 0. For an ion, the sum of all the formal charges equals the charge of that ion. So to give you an example here, you have the first structure, structure A. Hydrogen starts out with 1 electron. It doesn't have any of its own, and it's got a half of electron from the bond between a carbon. Its formal charge is 0. Carbon starts with 4. It has 4 bonds, half from one of those electrons from each of those 4 bonds. It has a formal charge of 0. Nitrogen starts off with 5. It has 2 from its lone pair. It has 3 bonds, so it gets an electron from each of those 3 bonds. Its formal charge is 0. Now, structure B, we have nitrogen in the center. Well, this is also breaking the rules because nitrogen is a smaller atom than carbon. You tend to have the bigger atom in the center. But well, what if we did have nitrogen in the center? So nitrogen has 5, has no lone pairs in this diagram. It would get half of each of the 8 bonding, so 4 electrons there, has a formal charge of +1. Carbon, on the other hand, starts with 4, has 2 from its lone pair in this structure B. It has 3 from the bonding, so it has a -1 formal charge. And which structure is better? Answer is structure A, because it minimizes the formal charge. And when you look at formal charges, these rules apply. I already mentioned that the sum of formal charges for a neutral molecule is 0. Sum of formal charges of an ion equals the charge of the ion, and the minimization of the formal charges are better than having large ones. When we cannot avoid having formal charges not be 0, put the more negative formal charge on the more electronegative atom. So there are some exceptions to the octet rule. One of them is odd number of electrons. So nitrogen monoxide, for instance. This means it has one unpaired electron. This is also known as a free radical, and these are also very reactive. So free radicals are used often in combustion, so you can stop combustion by removing the free radical chain reactions. There's also incomplete octets. So boron and aluminum can engage in bonding, and they don't necessarily have to have octets. And then expanded octets. So any element beyond period with period 3 and beyond. So the third row in the periodic table, these have empty d orbitals, and then they can have more than 8 electrons because after the third principal quantum number, there are d orbitals available for electron energy levels, but they are not currently occupied. So that's also left over from the quantum mechanical model of the atom. So which molecule expect to be a free radical? A free radical is going to have an odd number of electrons, and the one that has an odd number of electrons is D, the chlorine monoxide there, because chlorine has 7, oxygen has 6 electrons. The rest of them, nitrogen has 5, so these are all paired, and then carbon and oxygen, they both have even numbers. So it doesn't matter what number you have on there for those. That the chlorine there has an odd number of electrons, so having 1 chlorine, and then an even number from oxygen, that's an odd. Which molecule would you expect to have an expanded octet? So this has to be period 3 and above. So carbon, oxygen, and nitrogen, these are period 2. Hydrogen's period 1. Phosphorus is in period 3. So that's the one that has the expanded octet. So bond energies, this is the amount of energy it takes to break apart the bond in the gas phase. So it's always endothermic. So think of it, so you can break things apart, but it takes some bribe, and the bribe here is energy. So adding enough energy is something that it will atomize, it'll break apart. So, and with chemical reactions, this involves this exchange of atoms. So that means that bonds are breaking and new bonds are formed. So when we look at the overall change of the reaction, the enthalpy change for the reaction, we can look at the energy it takes to break bonds, and then the energy it takes to form bonds. So it takes energy to break the bonds, and then energy is released for forming the bonds. And from that, we can calculate their overall change in reaction, the energetics for the change in reaction. So some trends. So the trends in them, the more electrons the atoms share, the stronger the bond, therefore the more energy it takes to break them. So if you look at carbon and nitrogen, the more electrons they share, the harder it is to break the bond. And also, generally speaking, the closer the atoms are together, the stronger the bond. So, and that's a general trend. It's not exactly a smooth trend, but that's a general trend. And so looking here between the bromine and the different halogens, for instance. So here's a chart showing the different average bond energies. And you can use these to estimate the standard enthalpy change for reactions. And the idea is that it's the sum of the bonds that are broken, these are positive, minus the sum of the energies of the bonds formed. So the bonds formed is going to be exothermic, the bonds broken are endothermic. So that's the idea there. So, for instance, let's look at methane plus chlorine to make chloromethane and hydrogen chloride. So you can estimate this and why am I using the word estimate? Because it's average. There's the average bond energy. So these are the averages of all the bonds. So those are the charts where the averages. So it's as if you're breaking, for this one, it's as if you're breaking a hydrogen-carbon bond and breaking a chlorine-chlorine bond, but then forming a carbon-chlorine and a carbon-chlorine and a hydrogen-chlorine bond. So you can estimate it using that. The reaction between hydrogen and oxygen to form water is highly exothermic. Which statement is true? The energies and bonds that break during the reaction. The energy needed to break the required bonds is greater than the energy released. That's not true. The energy needed to break the required bonds is less than the energy released than the bonds before. That is true. The energy needed to break the required bonds is about the same. No, it is this one. So the energy released is greater than the energy it takes to break, which is the reason why it's exothermic. So the distance between different nuclei, this is known as the bond length. And the bond length, it depends on what else is around. It depends on the environment. We use the average bond length, and and these are averaged for similar compounds. Another thing, the averaging. So it depends. We look at a bunch of data and we kind of average them out. And in general, the bond length, the more electrons that are shared, the closer the bond. So you can use this with friendships too. You're like, this is my friend, this is my close friend. Like, ooh, this person's a close friend because we are much more strongly bonded. We share more electrons, just like carbon-carbon, kind of like a carbon triple bond. We are like a carbon triple bond. We share many things together. We're not a normal carbon single bond. We are a close friendship. We are a close bond. So those are the general trends in bond lengths. And generally speaking, the bond length decreases from left to right. But that's generally it increases going down. Also general, as the bonds get longer, they also get weaker. So you can see there's lots of generalities here because there's exceptions. And what would chemistry class be without exceptions to rules? So here are the bond lengths for the various elements and compounds. And thank you for listening. Please join us for more lectures.